Hi everyone, this is Lab 4 for circuits. The purpose of this experiment is to predict the behaviors of circuits containing resistors in series. We will use multimeters to measure the actual values of conventional current and potential differences in the circuits, and we will examine the behavior of ohmic resistors and capacitors. As for our previous results, we have that the current flowing through the loop containing 47 ohms and 100 ohm resistors is equal to 0.02 amps, and the experimental RC time constant was determined to be 8.59 seconds. For the fundamental principles, we have that energy conservation is utilized in the loop rule, which states that for any closed loop, the total sum of potential difference must be equal to 0. Charge conservation applies to the node rule, which states that the current entering a node must be equal to the current flowing out of a node. We also apply the principle that when in series, the total resistance is equal to the sum of all individual resistors. Ohm's law states that the change in potential is equal to the current times resistance. And lastly, linearization is utilized to calculate the RC time constant. For the experimental design, we have the system as a circuit and all its components, the surroundings is everything else, and as for assumptions, we have that the resistance of the wires and ammeter is negligible. For our supplies used, we have a multimeter, 2 batteries, resistors, a capacitor, and light bulbs. Circuit 1 is measuring current. For our initial conditions, we have 2 batteries, wires, a multimeter, and 2 resistors that are in series. The expected current was calculated as seen on the screen, and it came out to be 0.0204 amps. But then when we used our actual experimental setup, we found that the current flowing through the circuit was 0.02 amps. When the connections of the ammeter were reversed, the current reading was the same magnitude but negative, and this can be seen in the photo. The node rule applies here because there is only one wire coming in and leaving each node. Therefore, the current through each resistor must be the same. The circuit 1 setup was also used to measure voltage. We replaced the ammeter with a voltmeter to measure the potential differences at different points in the circuit. These measurements were taken according to the label diagram on the screen. It was concluded that the net potential difference throughout the whole loop was equal to 0 when starting and ending at point A. The current reading remained the same at 0.02 amps because current does not flow through the voltmeter due to its high resistance. Here is the graph of the potential differences measured on the last slide. These potential difference values and the current measured were used to calculate the experimental resistance of different components in this experiment using Ohm's law. The 47 ohm resistor had an experimental resistance of 50 ohms, the 100 ohm resistor had a resistance of 100.5 ohms, and both the wire and ammeter were determined to have 0 resistance. If the voltmeter had been replaced with the ammeter in parallel with the resistor, the current reading would have increased to 0.06 amps, since now only a portion of the current is experiencing resistance, since it is split at the node. Now we are working with a second circuit containing both a resistor and a capacitor. This circuit design was used to determine how resistance impacts charging and discharging of a capacitor. The initial conditions are listed. When the battery, light bulb, and capacitor are all connected, the light will quickly brighten and then die out once the capacitor is fully charged and current decreases to 0. When the batteries are removed, the light again quickly brightens and then dies out, indicating the capacitor is discharged. The charging and discharging times with a 10 and 20 ohm bulb are displayed. There are longer charging and discharging times with increased resistance because the resistor limits the flow of current, meaning it takes longer for the capacitor to accumulate charge. An RC circuit will now be used to determine the time dependence of voltage across a discharging capacitor. The initial conditions are listed. First, the capacitor is charged using the batteries. Then the capacitor is discharged and the voltage and time are recorded during this time. The data obtained is then linearized using natural log and the data is graphed. The slope of the plot is then used to calculate the RC time constant for the circuit. Here is the plot created from the capacitor discharging data obtained during the first 20 seconds of discharging. The slope of the graph came out to be 0.1164. From this value, the experimental RC value is determined to be 8.59 seconds. The theoretical value based on the resistance and capacitance of the materials used is equal to 6 seconds. As for sources of error, it was assumed that the resistance of the ammeter and the wire were negligible, but the resistance of these components may have impacted measurements. There may have been errors in obtaining measurements using the multimeter, resulting in inaccurate values being obtained. Errors could have also occurred during circuit setup, resulting in inaccurate measurements. Lastly, issues with stopwatch timing could have resulted in errors for the RC calculation. The answer to the first what-if question is that the actual ammeter used in this experiment most likely has some resistance instead of the 0 resistance it has in the virtual simulation, although the calculations in this experiment say otherwise. The experimental current measured should be lower than the theoretical value, which was very minimally observed in this experiment. As for the second what-if question, the answer is that the capacitor in the simulation charged instantly because there was no resistance in the wire. The real capacitor in this experiment took longer to charge than the simulation capacitor because the wires in this real experiment have slight resistance. The ammeter used also has some resistance, which explains the increase in charging time. As for the conclusions, we have that Ohm's law, the node rule, and the loop rule could all be tested and proven experimentally using real circuits. Currents and voltages are also time dependent. Thank you so much for watching.